video, I will demonstrate an AES 128 encryption decryption hardware software co-design on Cyclone V SoC. The system uses ARM Cortex A9 HPS to control the control and software decryption and the FPGA fabric for hardware encryption. So this is the block diagram of HPS FPGA. The HPS here will generate random 128-bit key and read plain text from the user and communicate with the FPGA through the memory mapped AXI interconnect, and the FPGA will perform AES 128 encryption and return back the ciphertext to the HPS, and finally the HPS will do decryption and should show the original plaintext. Perform the communication between the HPS and the FPGA. We will see that later. We will add a parallel input output slave and connect those the interface of those parallel input output to the AXI bridge, which is already connected to the HPS. I will use 4 by 32-bit input register for the plain text and 4 32-bit for key and output registers 4. So we will have 12 parallel input output to perform this procedure. And we will also need 2 registers for the control and the status to control the encryption and do handshaking between the HPS and the FPGA. And the clock will be 50 megahertz. This is the platform designer for our project. So as we can see here, those are the parallel input output added to the my platform designer, and the direction will be output since it goes from the HPS to the FPGA. We have 4 for the key, and we have 4 for the plain text, those in for the plain text, and ENC encoder, that's for the encryption output from the FPGA to the HPS. As we can see here, it's input. And as we can see here, it's exported to the main top level entity, top level module for the RTL. And on the same time, it's connected to the HPS to FPGA lightweight AXI master. So after generating HDL from the platform designer, we will get those registers, and with each register we will get address base. Those we will need those later to use those addresses in software in C, so we can do memory address mapping. We'll use all 32 bits for the in plain text, key, and encryption, But for the control and the status register, for the control, we will use 1 bit just for start, which is start signal from HPS to FPGA, and status signal from FPGA to HPS. This is our top level module in RTL and Quartus Prime. So, we and those are the exported conduit from the platform designer. And as we can see here, they are connected to the input signal and top level module. So those are the encryption output. As we can see here, those connected to the encryption signals, and the key are assigned here, and the plain text in are assigned here, and those are the control and the status signal, where here status conduit here, and the start is here. And those are the states for the RTL design. So we have like 4 states: when reset, idle, busy. When it's idle, it's ready to accept to read the plain text and key. And when it's busy, it's do encryption, and here it's done. And we can see it here in the RTL. So this is the clock, and this is the HPS. It's a reset signal from the HPS to FPGA. So if the reset is activated, all the control, status, and input output register will be 0. And if it's not resetted, and we will get the start signal from the HPS, and if it's not busy, it will latch the input plain text and key, and then goes to busy. And when it's busy, it will do the encryption and put the encrypted the register. That was the hardware part of the design. And for the software, this is the software part. So what the software will do, we will map the FPGA register here using this function mmap, using the virtual base. And as we talked before about the address bases extracted from the FPGA or from the RTL in Platform Designer. So on the RTL, we should so in RTL, after we finish the Platform Designer HDL generator, we will get we need to update those HPS, the header files, because those header files will contain the base addresses we need in software. And those are the address bases here. And then we need to read a plain text from the terminal, and this is how we read the plain text here. And then we need to generate a random key. Here, the random key generation. And later, we will need to send this key, the key generated here to the FPGA on this address pointer. This is for the key, and this is for the plain text, and this is the control signal we are created here. This is the control for the start. So after sending the key and the plain text, we will change the control signal to 1. Then when it's done, it will we will get the encrypted registers value here. This is the encrypted from FPGA, and we will print it on the terminal. After we finish compilation of the RTL design, so we will download it to the CycloneV. After that, we need to compile the C design. So this is the EDA. So this is Embedded Design Suite by Altera SoC EDS. And this is the directory of our C file. And we can compile it here. And then, so we have this executable file here generated. And after that, we'll need to export this executable file by USB stick and put it on the board so we can run it there. So we will use PuTTY. It's a remote Linux terminal window to run the executable file. So this is the where we put the executable file here, and we can run it. And here the the operating system asks to input the plain text, and I will put my name and run it. And as we can see here, this is the key generated, and this is the original plain text, and this is the ciphertext from FPGA. And as we can see here, it's also match the software encrypted. And this is the original plain text.